Diode. A diode looks something like this, and it comes in different sizes. They typically have a black cylindrical body that has a stripe at one end, as well as some leads coming out to allow us to connect it into a circuit. This end is known as the anode, and this end is the cathode, but we're going to see what that means later on in this video. You can also get other forms such as a Zener diode or an LED, which is a light emitting diode, but we're not going to cover those in this video. A diode allows current to flow in only one direction in a circuit. If we imagine a water pipe with a swing valve installed, as water flows through the pipe, it will push open the swing gate and continue to flow through. However, if the water changes direction, the water will push the gate shut and this will prevent it from flowing. Therefore, water can only flow in one direction. This is very similar to a diode. We use them to control the direction of current in a circuit. Now, I've animated this video using electron flow, which is where the electrons flow from the negative to the positive. However, you might be used to seeing conventional flow, which is traditional in electronics engineering, and this is where the electrons flow from the positive to the negative. Electron flow is what's actually occurring, but you might come across conventional current still, as these explanations are easier to understand. Just be aware of the two and which one we're using. So if we connect a diode into a simple LED circuit like this one, we see that the LED will only turn on when the diode is installed the correct way. And that's because it allows current to flow in only one direction. So depending on which way the diode is installed, this will act as either a conductor or an insulator. In order for the diode to act as a conductor, the stripe end is connected to the negative and the black end is connected to the positive. This allows current to flow. We call this the forward bias. If we flip the diode, it will act as an insulator and the current can't flow, and we call this the reverse bias. So how does the diode work? As you may know, electricity is the flow of free electrons between atoms. We use copper wires because copper has a lot of free electrons, which makes it very easy to pass electricity through. We use rubber to insulate the copper wires and keep us safe because rubber is an insulator, which means its electrons are held very tightly and they can't therefore move between other atoms. If we look at the basic model of an atom for a metal conductor, we have the nucleus at the center, and this is surrounded by a number of orbital shells which hold the electrons. Each shell holds a maximum number of electrons, and an electron has to have a certain amount of energy to be accepted into each shell. The electrons located farthest away from the nucleus hold the most energy. The outermost shell is known as the valence shell, and a conductor has between 1 and 3 electrons in its valence shell. The electrons are held in place by the nucleus, but there's another shell known as the conduction band. If an electron can reach this, then it can break free from the atom and move to another. With a metal atom such as copper, the conduction band and the valence shell overlap, so it's very easy for the electron to move. With an insulator, the outermost shell is packed. There's very little to no room for an electron to join. The nucleus has a tight grip on the electrons and the conduction band is far away, so the electrons can't reach this to escape. Therefore, electricity cannot flow through this material. However, there's another material known as a semiconductor. Silicon is an example of a semiconductor. With this material, there's one too many electrons in the outermost shell for it to be a conductor, so it acts as an insulator. But as the conduction band is quite close, if we provide some external energy, some electrons will gain enough energy to make the jump from the valence and into the conduction band to become free. Therefore, this material can act as both an insulator and a conductor. Pure silicon has almost no free electrons, so what engineers do is dope the silicon with a small amount of another material to change the electrical properties. We call this p-type and n-type doping. We combine these doped materials to form the diode. So inside the diode, we have the two leads, the anode and the cathode, which connect to some thin plates. And then between these plates, there is a layer of p-type doped silicon on the anode side and a layer of n-type doped silicon on the cathode side. The whole thing is enclosed in a resin to insulate and protect the materials. Let's imagine the material hasn't been doped yet, so it's just pure silicon inside. Each silicon atom is surrounded by 4 other silicon atoms. Each atom wants 8 electrons in its valence shell, but the silicon atoms only have 4 electrons in their valence shell, so they sneakily share an electron with their neighbouring atom to get the 8 they desire. This is known as covalent bonding. When we add in the n-type material such as phosphorus, it will take the position of some of the silicon atoms. The phosphorus atom has 5 electrons in its valence shell, so as the silicon atoms are sharing electrons to get their desired 8, they don't need this extra one. So there's now extra electrons in the material and these are therefore free to move. With p-type doping, we add in a material such as aluminium or aluminum. This atom has only 3 electrons in its valence shell, so it can't provide its 4 neighbours with an electron to share, so one of them will have to go without. There is therefore a hole created where an electron can sit and occupy. So we now have 2 doped pieces of silicon, one with too many electrons and one with not enough electrons. The 2 materials join to form a p-n junction. At this junction, we get what's known as a depletion region. In this region, some of the excess electrons from the n-type side will move over to occupy the holes in the p-type side. This migration will form a barrier with a buildup of electrons and holes on opposite sides. The electrons are negatively charged and the holes are considered therefore positively charged. So the buildup causes a slightly negatively charged region and a slightly positively charged region. This creates an electric field and prevents more electrons from moving across. The potential difference across this region is about 0.7 volts in typical diodes. When we connect a voltage source across the diode, with the anode, the p-type, connected to the positive and the cathode, n-type, connected to the negative, this will create a forward bias and allow the current to flow. The voltage source has to be greater than the 0.7 volt barrier, otherwise the electrons can't make the jump. When we reverse the power supply so that the positive is connected to the N-type cathode and the negative is connected to the P-type anode, the holes are pulled towards the negative and the electrons are pulled towards the positive, and this causes the barrier to expand. Therefore, the diode acts as an insulator to prevent the flow of current. Diodes are represented in engineering drawings with symbols like these. The stripe on the body is indicated with a vertical line on the symbol, and the arrow points in the direction of conventional current. When we look at a diode, we see these numbers and letters on the body. These identify the diode so you can find the technical details online. The diode will have an IV diagram that looks something like this. This diagram plots the current and the voltage characteristics and forms this curved line. This side is how it should perform when acting as a conductor, and this side when acting as an insulator. You can see that the diode can only act as an insulator up to a certain voltage difference across it. If you exceed this, then it will become a conductor and allow current to flow. This will destroy the diode and probably your circuit, so you need to make sure the diode is sized correctly for the application. Equally, the diode can only handle a certain voltage or current in the forward bias. The value is different for each diode, and you'll need to look up this data to find the details. The diode requires a certain voltage level to open and allow current to flow in the forward bias. If we apply a voltage less than this, it will not open and allow current to flow. But as we increase past that, the amount of current that can flow will rapidly increase. The diodes will also provide a voltage drop into the circuit. For example, when I added this diode into a simple LED circuit mounted in a breadboard, I get a voltage drop reading of 0.71 volts. So why do we use them? As mentioned, we use diodes to control the direction of current flow in a circuit. That's useful, for example, to protect our circuit if the power supply was connected back to front. The diode can block the current and keep our components safe. We can also use them to convert alternating current into direct current. As you might know, AC or alternating current moves electrons forwards and backwards, creating a sine wave with a positive and a negative half. But DC or direct current moves electrons in just one direction, which gives us a flat line in the positive region. If we connect the primary side of a transformer to an AC supply and then connect the secondary side to a single diode, the diode would only allow half the wave to pass, and it would block the current in the opposite direction. So the secondary side of the circuit experiences only the positive half of the cycle, so it's therefore now a very rough DC circuit, although the current pulsates, but we can improve this. One way to do that is if we connected 4 diodes to the secondary side. We create a full wave rectifier. The diodes control which path the alternating current can flow along by blocking or allowing it to pass. As we just saw, the diodes allow the positive half of the sine wave to pass, but this time the negative half is also allowed to pass, although this has now been inverted to turn it into a positive half also. This gives us a better DC supply because the pulsating has greatly reduced. But we can still improve this further. We simply add in some capacitors to smooth out the ripple and eventually get it to a smooth line, closely mimicking a DC supply. We've covered how capacitors work in great detail in our previous video. Do check that out, links down below. So how do we test a diode? So we take our diode and our multimeter. We connect the black probe to the end of the diode with the stripe. We then connect the red probe to the opposite end. When we do this, we should get a reading on the screen. For example, this model 1N4001 diode gives us a reading of 0.516 volts. That is the minimum voltage it takes to open the diode to allow some current to flow. If we now reverse the leads connected to the diode, we should see OL on the screen, which means outside limits. That's telling us that it's not been able to make a measurement, and that's a good thing, because it means it can't complete the circuit, so the diode is doing its job. If we were to get a reading connecting on both configurations, then the component is faulty and shouldn't be used. To test the diode in a circuit for voltage drop, we simply move the multimeter into the DC voltage function, and then we place the black probe on the striped end and the red probe on the black end. This will give us a reading, for example, of 0.71 volts, which is